reviewers process and now let's examine it.
So yeah, you probably all know me by now. I'm Sean, and I've been working on a 45 credit master's thesis looking at magnetites and using laser ablation to try and unravel the trace element patterns for the ore petrogenesis. So when I started, there was two things I asked myself, and it was, why am I choosing this thesis title? And also, what do I want to investigate and what have I now investigated? So the reason why I've chosen this thesis title is because the idea around Kiruna-type deposits is so widely debated. There's a lot of different ways of thinking on how this actually formed, and I'm trying to just understand and hopefully find an answer by using trace elements and creating different diagrams and using old data and also some fresh new data of my own. And what have I investigated? Well, there's a lot of things I've taken into account. I've looked at a lot of different elements, placed them in a lot of different softwares, created a lot of different diagrams, which you'll see. And yes. So there are a few aims I wanted to have when I started this, and that was I wanted to be able to compare different types of data to get this environment for how this formed, and just to try and make it visually nice for people that are going to be looking at it, because there's a lot of data that's actually included. So I've used data from Grängesberg and Kiruna, both in Sweden, new data supplied. Kiruna data was supplied by Sakti from India, and Grängesberg from Van Control, Högdal, Jonsson, and Sun. And this is important because this is the first time ever Grängesberg data has been used in this field of geology, because more often than not it's to do with other data. Because of Kiruna-type deposits, people like to use the type locality, which is Kiruna, which I'll get to. So the things people wanted to try and understand was, is this automagmatic, or is this more hydrothermally formed? So what will I talk about in this presentation? I'm going to be talking about the geological backgrounds of the different areas I've studied. So as I said before, the localities in Sweden, Grängesberg and Kiruna. I'll also be mentioning El Laco in Chile. I'll be mentioning Bafk in Iran and Gousha in China. I'll then be talking about the methodology, what I did with the data, how I analyzed it, how I put it into relevant diagrams. And that will lead us on nicely to the results. I'll be showing you the diagrams I've made, and while I'm doing that, I'll also be discussing what these show or what it can imply. And that'll lead us on very nicely into the conclusion, where I'll try and wrap it all up for you and see if we can actually understand what has happened with Kiruna-type deposits. So Kiruna-type deposits, where are they? They're also known as apatite iron deposits. So for those of you who may not be aware of where these are, we have Kiruna up here, Bergslagen, which is where Grängesberg is, which I'll get into more detail with that later. Gousha in China, Bafk province in Iran, and El Laco in Chile. So Kiruna-type deposits. Kiruna-type iron ore is the most important iron ore deposit in Europe, and this is why it's very important to try and understand how this may form, because it's so important and it's used every day. It's used in all infrastructure. It's very well known for its high-grade magnetite. It contains 60% iron, which is a lot, and phosphorus contents below 2%. When I was in Kiruna myself, I saw a 75% iron exposure at 1,350 meters depth. They are commonly known as apatite iron oxide deposits, for they are associated with apatite. And as I said before, most commonly known as Kiruna-type deposits because of the Kiruna mine in Kiruna, northern Sweden. So Kiruna in northern Sweden is in Norrbotten and is the most productive mining area in Europe. It's found in the northern part of Fennoscandian Shield and is situated within an Archean basement, which is covered by Proterozoic rocks of volcano-sedimentary origin, which is an important point to remember as we move on in the presentation. And the ore body itself is huge. It spans over 4 kilometers. It has a 60 to 70 degree dip to the east, so just flip this diagram on top right. Can be found up to 100 meters thick, but towards the top, when they first started, it was found 200 meters thick in places. It's dominated by magnetite and apatite, as you can see here, magnetite and apatite, and sometimes the apatite is found in dikes, and is known to host some rare earth elements as well, which are not, as I know of, economically viable to take, but they're working on it. And the age is of around 1.9 to 1.8 billion years old, thanks to lead uranium dating. And since they've started mining in around 1880s, they have managed to extract over 2 billion tons of ore. So that leads us on to the next locality, Grängesberg, in central Sweden. So if we look on the map, there we are now in very sunny, dry Uppsala, tropical weather. And this area, Grängesberg, is found within the western part of the mineralized Paleoproterozoic Bergslagen province. Bergslagen is where I showed you on the previous diagram, because this is the whole area. This is where it's called Bergslagen. And this area itself is very heavily mineralized. And this is where you find a lot of different mines like Garpenberg, Sala, Luisgruvan, down here Zinkgruvan, and this is where Grängesberg is. So it's found within the central southern Sweden extension of continental back arc magmatic region, that's a mouthful. And of the 6,000 known metallic mineral deposits in Bergslagen, so of all of these dots here, blue and red, of all 6,000 of them, 5,500 of them are believed to be iron oxide deposits. And this area is known as the Grängesberg Mining District, the GMD. And the ore dips 50 to 70 degrees southeast and reaches depths around 1,700 meters. Not as impressive as Kiruna, but still pretty big. So Gousha in China is found in the southern part of the Ningwu Basin in the Lower Yangtze River Valley in China. And this area is known for its important resources of copper, gold, iron, and sulfur. And this is found within magmatic rocks also. And mining began in around the 1950s, so it's a relatively young operation compared to the others. So the geology of this area, as I said before, southeast of the Ningwu volcanic basin. So here we are here. Is the Yangtze River. It's in an uplifted region of the basement, formed in the late Jurassic to early Cretaceous. And the basement rocks again, very old, 2.9 to 1.8 billion years old, archaean. Magmatic activity is believed to be influenced by large-scale fault and folding, and the deposit as a whole is fully exposed. So I'll get to that when I come to talk about my samples. But yeah, if you look here on the image here, Gousha is one of the biggest iron mines in that region. So Bafk in Iran, it's found within the Kashmir-Kurman tectonic zone, and it's known for having 34 mineralizations, and they hold up to 1,500 million tons of iron ore. And these deposits are found similarly with the Goushan ones, as I should have stated, as massive veins or stockwork ore. And you also see that in Grängesberg as well. And again, there is also evidence of hydrothermal overprinting here, but that is mainly through microscopic analysis, and you see that thanks to brecciated textures. So the next locality is El Laco in Chile. Very dry, very high altitude area. And Oval believes that, he conducted studies of samples, and the difference between this locality and the other localities I've mentioned is the samples are not only from the surface, but he was able to get drill core samples as well and implement that data from there. This area is found on very thick crust, 58 to 76 kilometers, and hosts world-class deposits of magnetite that host both subvolcanic and volcanic features. I'm not lucky enough to be there, to have visited there, but I know you have. Ore bodies have hosted, are believed to host over 700 million tons, again, huge. And the magnetite there has an average grade of 49.2, not as high as Kiruna's, but Kiruna is just an insane example. And there is evidence for intense volcanic hydrothermal alteration as well. So the methodology, what did I do with my data, or what did I want to get? So I used electron microprobe analyzers and also backscattered electron imaging. As you can see here, there's some lovely euhydromagnetite there from Gränges Bay, and also you see some nice magnetite here from Kiruna. They look very similar. I then had samples from Gousha and Gränges Bay that were used using laser ablation inductively coupled plasma mass spectroscopy, that was sent to China itself. And yeah, they conducted that in the lab because there's only a few places in the world where this can actually be done. And this data was sent back to me then as a spreadsheet which I could then manipulate. And this data that I was then able to use, I then placed into relevant diagrams, which are called discriminant diagrams. So this data I've got, which was then, at the time, the Gousha one was relatively new, but has now been used in Sun et al.'s paper recently. But the Kiruna data that I had from Sakti is new, and the Gränges Bay data is very new. Yeah, so what did I get? So I put the data from Gränges Bay into a trace element diagram because I wanted to try and see if there were any trends. So as you can see from the legend, these just correspond to just these sample names, and they all came from a very similar location. And what's interesting to see here is that there is a calcium negative decrease, and that is typical of hydrothermal influence. So when I saw this, I thought, okay, maybe these Gränges Bay samples have maybe formed hydrothermally. But then I looked at the other data, and these four here. So you have magnesium, aluminium, titanium, and also manganese here. And all four of them are relatively high. And that indicates a consistent magmatic environment. Oh yeah, one thing to mention is there's this chromium. This chromium does this for some reason. I need to look into that. So I then put data from Gränges Bay and Gousha into a rare earth element diagram just to play about. And what kind of shocked me was the fact that this Gränges Bay RA6 sample is just so obscure compared to the rest. I saw this back in January, and I still haven't managed to understand why it's done that. But all of them have this European negative anomaly, and the Gousha brecciated and massive ore start very high. They were normalized next to those rock chondrite values. And the vein hosted ore fluctuates pretty crazy actually. This could be due to later influences, maybe hydrothermal activity, but I'll have to look into that. So this is the diagrams that I put almost all my data into. There's data from Gousha, Kiruna, Gränges Bay, Bafk, Los Collorados in Chile, Nangling Valley as a control, and then I added all the data from Oval's paper. And the reason why I didn't just call it El Laco, like I've called it Bafk, or I've called it Gousha, or I've called it Gränges Bay, is because of the drill core samples. So what I wanted to try and show is where the drill core samples plot compared to the surface ones as well, just as a comparison. So if we start to add a few clouds onto here, this is the Kiruna one, and then this followed by the Gränges Bay one. then the Gousha one, the BAF one, and we have the drill core samples there within the porphyry field, followed by the control, which was the skarn deposits from the Nanling Valley. And what's interesting to see is I added these values to see if this template from Dubuis and Bowden would be viable, would be good, would be worth making with my data. And thankfully, these skarn deposits do plot within this skarn field. And then if we start to then add arrows to try and visualize a trend for each data set, we start to see that Kiruna goes from the iron, titanium, vanadium field and then starts to move towards IOCG or skarn, you could say. Gränges Bay has a similar trend. It's going from a more, let's say, magmatic source to a more hydrothermal. Similarly with Gousha, sorry, and then with Bafk as well. So yeah, I think Bafk shows it very well. Moving on, this was for the calcium, aluminium, and manganese. Moving on, we then have a nickel, chromium, manganese, and titanium, vanadium discriminant diagram. This time I did not use the Chile from Eval because I didn't have enough data here for some of the samples, if any. So instead of putting it in, I just kept it like this to make it easier to visualize for everyone. So there's the Kiruna field. There's the following Gränges Bay field. There's the Gousha field, the Bafk field, and there's the skarn from the Nanling Valley. Again, plotting perfectly, not one is outside of this field. And again, let's start adding some arrows. You get to see that the Kiruna again moves from the titanium, vanadium, iron field towards the ICG and the banded iron formation. One could say that the trend is actually curved, like this, so we would eventually come here. Similarly with Gousha, I think Gränges Bay shows a very nice trend. And again, you get to see this trend with Kiruna. So this is a very nice diagram. I'm very proud of this diagram. I do say so myself. This is a titanium to vanadium ppm diagram. And I got these clouds from Knippen et al. What I really like about this diagram is the fact that you get this overlap area where both fields meet. And if you look again, Kiruna starts up here deep into the igneous field. Similarly with Gousha, similarly with Gränges Bay, and you get some Bafk as well. And they all have this trend going across here where they all end up, there's clusters here, especially with Gränges Bay and Gousha, where they are found within this overlap between the igneous and hydrothermal. And then you get this continuation of this Kiruna into this zone here. You also see it as well with ones from El Laco and the drill cores here. And what I said at the beginning was that people didn't know if it was orthomagmatic or hydrothermal or a bit of both, or if there was predominantly igneous at the beginning and then a later introduction of hydrothermal activity. I think the good thing about this diagram is that it does show a clear trend, and it does show that you start with a igneous source. You know, this Kiruna, this Gousha, this Gränges Bay, and as time goes on, they start to move towards the hydrothermal area, not into it like this skarn, but this way, where this is where you probably get the later hydrothermal influence, which can give us the features that we do see. And this is where it leads us on to where I'm going to conclude. I think that the analysis that we did and the analysis that can be done looking at this data is the right way to go about it when trying to unravel the history of these deposits. Because the diagrams we've managed to create do show trends. There is that depletion in calcium which may indicate hydrothermal activity, but it doesn't necessarily mean that that is the only mechanism that was involved in the system. And that's why you see this magmatic origin with later hydrothermal influence as seen in the previous diagram. So what I believe is that there was originally a volcanic system which is why you get these samples in Kiruna, these quartz-bearing samples. And then later on, you get this hydrothermal influence, which you find here, also in Kiruna. Bear in mind, these are both in the hanging wall in Kiruna. And I think that this is what you get later on as the volcanic system starts to cool down and you get these later hydrothermal influences, which may cause processes like metasomatism and other things alike. But thank you very much for listening, and if anyone wants to read all this, that is my reference list. Thank you very much. I need some paper, I just poured some water on your laptop.